Hello, puppies and kittens. I'm here again with Dr. Jonathan Baker, and he had an idea. Why not call in from work and show us what he does? So he's a paleoclimatologist, and so he does radiometric dating. And right now, he has a sample that he has a curiosity about. Jonathan, would you please explain this?
Sure. Good to see you all. I've been in China the last couple of weeks and doing what we do on this lovely thermoscientific Neptune Plus behind me. It's a $500,000 machine whose main job is to measure very precisely isotopes of different elements. In this case, we'll be measuring uranium and thorium isotopes. And that's to figure out the age of a cave sample. I can't tell you where it's from. I'll just say it's in Europe. That's relevant because it's influenced by what's happening in the North Atlantic. It's connected to the North Atlantic climate, just like the Greenland ice cores are connected to the North Atlantic climate. So I'll come back. I want to explain a bit more about that, but I'll just show you now. What we have here is the result of a 12-hour chemical process to reduce our sample and collect the thorium in one vial, the uranium in another vial. We'll measure those separately. So I'm just going to set up the measurement for the thorium, and while that's running, I'll explain what's happening.
Okay. I'm curious how he managed to how do they extract the thorium and uranium and all of it from whatever it is that they found.
So we add a bunch of acids. This is from a calcite mineral. Calcium carbonate reacts with any acid, just like baking soda and vinegar. And by adding these acids progressively, we get rid of the stuff that's soluble, including organics that might interfere. And we end up leaving just the, let's call it, and we can separate out by precipitating the thorium and uranium with iron together. We can trap it out and get rid of everything else. So like I said, it's about a 12-hour process, just going back and forth between the acids, drying it down at boiling temperatures. Oh, this is ready to go. You can see our signal here, very nice. So I'm gonna start the analysis right now. Yep. So when we get rid of all that, we can isolate the thorium in one vial and uranium in another vial. Hopefully we've gotten rid of everything else. So what's happening now is it's going to run this through a plasma flame at some 10,000 degrees and just ionize the sample. So it's using a carrier gas to send that through the mass spectrometer. And what's really being measured here are voltages at the end of the cups. These are ionized atoms, and so they've got an extra electron and they produce a voltage across the collector cup. So every little jump here, it's measuring those isotopic ratios. We're going to do that about 200 to 300 times. It doesn't just take one sample, it takes lots and lots and lots of them, and takes all those measurements and statistically reduces it down so that we have a median and an uncertainty window. We can tell already by this number here, which is 1.35 times 10 to the minus 2, that this does contain a lot of thorium that was produced radioactively. I mean, from the decay of the specific isotope of uranium, 234. So 234 uranium decays into 230 thorium with a half-life of about 245,000 years. Right, so this is a short enough half-life that we could analyze samples that are relatively young, meaning less than 1,000,000 years old. Right? Is that appropriate to say relatively young? It's only,
Well, from
half.
my perspective, yeah.
Yeah. Okay, so now that that's running, it's going to take a few minutes. So I'll explain what I'm doing. We don't know the age of this sample. I've never analyzed it before. And I just wanted to show people first, like, what does this actually look like? I'll probably produce another video when I get back home showing a bit more of the process so you can see, like, what does radiometric dating actually look like? It's kind of a black box. I mean, you've seen, the formulas mathematically, how does it work? But, what does it actually look like in the lab is a different question. So because we don't know the age of the sample, I mean, we could get any result, really. I can't control the result. There's no magic button I can hit here to adjust the age if I don't like it. It's just going to measure what the isotopic ratios are. This sample is interesting, though. Like I said, it's from Europe, influenced by North Atlantic climate. And if I can switch the camera around here, it's a little awkward here, but let's see. This is the Greenland ice core, the main Greenland ice core. It's from the center of the ice sheet, approximately. And all these ice cores have this shape to them. This is the modern day, and this is going back about 100,000 years. And you see, this is the warm Holocene period, as we call it. This is the interglacial, right? The last ice age just ended, and this is the nice warm climate we enjoy today. But there's this little dip here. You see
Now
that?
that started around that just for clarity, that started around 11,500 years ago.
Yeah, 11,650 years, according to the ice core records. And we define the beginning of that by the uptick here. See, it has this little dip down and it comes back up. This is called the Younger Dryas cooling event. It shows up in all the ice core records. And from our best understanding, it's a period where circulation in the North Atlantic kind of shut down or slowed down significantly, and sea ice expanded, and it got much colder overall. So Europe would be colder, Greenland would be colder. A lot of the rest of the world would be either colder or drier during this time, with a few exceptions. So that marks the beginning of what's called the Holocene epoch at the end of the Quaternary. We know the age of this dip here, this Younger Dryas event, by counting ice core layers, right? We count them in seasonal bands. There's a winter layer that forms, then a summer layer that's got some melt in it, and then a winter layer, a summer layer, a winter layer. By counting those bands, that's, we've literally visually counted 11,700 bands to the beginning of the Holocene, and about 12,800 to the beginning of the Younger Dryas. Let me
Now
show you.
is that absolutely precise?
No,
That
that's a
it
good
has to
question.
be?
So there are uncertainties. In fact, you see this little box here that shows the relative uncertainty of the ice core counting, because it is possible that some of those layers are not perfectly distinguishable. Some of them might not actually be annual, and so we compare all the different ice cores to get a sense of how uncertain our counts are. Um, This is just a close-up of the Younger Dryas event. You can see it begins here. Let's call it 12,000, almost 12,900 years ago. And it ends here about 11,700 years ago. So the sample I'm running now has this same curve to it. And because of, based on that curve, I'm predicting that the age of this sample should be about 12,800 to 12,900 years. Does that make sense?
Yes.
And I mean, I don't know. We'll see if it works. But that's my prediction based on the oxygen data in our sample versus the oxygen data in the Greenland ice core. Now, let's take this back to, say, a young Earth creationist perspective. They would have to suggest that this ice core formed within the last 4,500 years. And so when we count 12,000 bands of ice, these can't really be annual bands, right? And I mean, to be honest, we don't just count them visually, like, oh, there's a layer that looks different from this layer. That's one step, but there are like 2 or 3 dozen methods that we use to confirm these are actually seasonal bands. We look at the amount of dust. We look at other isotopes like nitrogen, argon, oxygen, hydrogen. We look at the amount of sodium, potassium, calcium that is in the ice, right? So there are many different ways. If I can come back here. There are many different ways to confirm. Ooh, our thorium just finished. That these are actually seasonal bands. But just for the sake of discussion, let's like take the creationist claim seriously and say, what if these are not annual bands? What if they did really form in the last 4,500 years? So the way we're going to test this is with this sample here. Our thorium just finished running, so we're going to switch it to uranium in a moment. These processes have nothing to do with each other. We're dating this sample by the decay of uranium into thorium inside of a cave that is, thousands of miles away from the ice core. So they're completely unrelated processes. One is radiometric dating right here. The other is this band counting method. And they don't influence each other. So this is as good of an independent corroboration as we can get.
How many times, I mean, how often do you get an opportunity like that where you get to the counting of the bands versus the radiometric age to compare these? How often does that happen?
If you're looking at samples less than 20,000 years, I'd say it's pretty often because we can collect data from across North America and Europe and in the Mediterranean.
Okay, so I just want to verify. You're saying that it has happened over and over and over again, that you've counted the annual layers and the radiometric dates also confirm that these are 20,000 years old.
I could probably find 500 studies within a 5-second Google search on Google.
But just 500? Okay,
Oh,
but 20 seconds. Okay. I just wanted to know, I just want people to realize how ridiculous it is when they want to argue that this one time that you counted two bands when it was really one atom, and so therefore everything is off. But it's hundreds of times that you've been able to confirm both methods over and over again, and not just in your lab, but in all types of labs that are doing the kind of work that yours is doing. Is that correct?
I would say, yeah, that's accurate. And those studies are published. They're out there for anybody to find and read. I'm happy to try and share some specifics, but here we're going to do it in real time. Like instead of just reading a published study, let's see it happen before it's even published. I don't have the chance to hide the data if they don't agree, right? You're going to see in real time what the results are. So our thorium just finished analyzing, and now we're going to switch over to uranium. All right. So I lost my train of thought here. Okay. Right now, this is kind of cool. Right now, it's measuring the intensity of 235 uranium. And that's the red line down here. And so I just put it into the sample. So if I did this right, and I actually captured the uranium, this red line should jump up here to between 6 and 7 millivolts. That's the ideal intensity that we want so that we could measure it. It takes a bit of time, though, for it to run through this little tube and finally get into the machine. So here it's jumping up.
I cannot see the line moving. We're going to need to move that camera up higher.
Can you see that?
Yes, I can see it now.
Okay. So it's jumping just above 6. I think that's pretty good. So we can go ahead and start this.
And once again, what was your prediction about the outcome?
I'm going to say 12,850 years, because it should be close to that start age.
So if it's 12,848 years, then you failed.
Oh, no. Let's say within 50 years of that, because we don't know exactly where it falls on that little curve. But 12,900 to 12,800, I hope it should be in there.
Okay.
I mean, that's about the start of the younger Dryas event.
And tell people, what is the younger Dryas event?
Sure. Let me name my sample here.
And I have to throw in a little bit of the woo kind of thing, because I remember reading that there's a in Canada, there's an impact like an asteroid impact that was also
Yeah.
dated to the same time. And I was reading about these people talking about whether there was a correlation in our environment, our environmental change as a result of that.
Let's split this in the observations and the interpretations. The observation is we see evidence of widespread cooling in the mid to high latitudes. So if you're North America, Greenland, Europe, Russia, it gets colder about this time by all kinds of different proxies, whether we look at plants or the chemistry of minerals like this, or in ice cores. We have evidence that in the North Atlantic, this overturning circulation slowed down. So the currents that normally bring warm water from off the Caribbean coast all the way into the Arctic, those slowed down. So there's less warmth coming from the tropics into the high latitudes. Uh, and we know the timing, I think, very well. Uh, the response of that varies around the world. If you look in the tropics, the response is generally drying of the climate. So if you go to, say, Southeast China, to South India, places that have this tropical summer monsoon, that monsoon weakened substantially. So there was less of this monsoon rainfall during the younger Dryas. So you get a varied response depending on which region you're looking at. Those are our observations. Our interpretation is that this was triggered mainly by melting of the ice sheets over Canada and Greenland. And at this point, they melted quite rapidly during the previous warm phase. And that fresh water, the addition of fresh water into the North Atlantic, altered the circulation strength by making it a little more fresh than normal. The saltier water is denser and heavier, so it can sink, and it pulls that water down. By pulling that water down in the Arctic, it pulls the subtropical water up to the north. Uh, and so that's the mechanism, principally, that we think is responsible. There is an impact associated with this, a couple of impact events. Um, I'm not convinced that the timing of those impacts supports that they could be a trigger. They could have contributed or exacerbated the cooling, but I don't think, in my opinion, is that's not the primary cause.
Okay, well, the asteroid impact is not the most woolly comment that can be made about the younger Dryas. I've heard all kinds of crazy things about it, including from the Atlantean believers. You know, help us understand what is the younger Dryas, because I'm a little confused myself. I thought it was when the profound cooling had kind of come to an unexplained and more or less abrupt end.
Um, so at
When it
this
when
point,
it went from deep freeze, 2 miles of ice on top of Chicago to
well,
or two
it's quite
kilometers.
less dramatic than that, for sure.
Okay.
Uh, at the peak of the last ice age, which is about 21,000 years ago, that's when we had the farthest southward extent of those ice sheets over Canada, the Laurentide ice sheet, as we call it. So that extended down into pretty much the U.S.-Canada border. It comes down further in some parts, like Wisconsin and out in Montana. But I mean, so it's quite extensive. That retreated back between 20,000, 19,000 years. It started melting and retreating backward, retreating northward. And that continued until 14 to 13,000 years when we get this abrupt, it starts warming a little bit faster than normal. And we think that warming may have prompted more rapid melting, but also the formation of, say, big lakes that are dammed by ice, right? So if you just have ice holding back the lake and that ice melts, then the dam breaks and that water's got to go somewhere. We do see evidence.
I forgot the name, but they were in Washington State. There's two massive glacial lakes that
Right.
some 17,000 years ago it caused super floods.
So yeah, this is like Glacial Lake Missoula, and we've got a couple others like associated with Lake Bonneville that did release lots of water at once. And in the Pacific Northwest, the evidence of that is flooding of the land surface. That water, though, all that fresh water, it doesn't impact the climate so much because it doesn't dump into like a main current that's affecting the climate. What
For
really
anybody listening in who they don't understand the gravity of this, when you say a lot of water at once, we're talking about a mile-high tsunami
it's
rolling in from inland, from the mountains.
well, if you could take one of the Great Lakes of the U.S. and just dump them out over the continents, it's something more comparable to that.
Yeah,
I,
because if I remember, Lake Missoula was at one point larger than Lake Superior, and so just imagine pulling the plug, you break the ice wall that holds this all back, and the evidence shows that there was a profound flood of incredible depth. And I don't think it was actually a mile, but it was very close to that. I mean, it's just a massive wall of water coming in from the mountains and destroying everything, creating the scablands, for example.
yeah,
And then the same sort of thing, oddly enough, happened from Lake Bonneville, although not like Lake Missoula did it like over a dozen times. It kept, the ice would freeze, the lake would build up, it would get up to a certain point where it would bust through the ice again and then flood everything, and that happened over and over again. But
right.
Bonneville, I think, only did that once or maybe twice.
It was less severe, but you do get these episodes where it drains out progressively, and we get different high stands. I spent a lot of time living in Utah, and you can see those right up on the mountains, the different lake levels, and it's pretty cool. So we are ready to go if you want to
Okay,
take.
go ahead.
Let me switch back the camera again so you can see what I'm seeing. Okay. So these are our thorium data, and every little row, every cell here is giving us the like how many times it counted that isotope in a second, right? So we've got 265,000 counts of this isotope, 5,057 counts of this isotope, and so forth. So we're going to take these data. This is the tedious part, to be sure.
That's the
But
tedious part. You're doing it with a computer. Can you imagine doing that by hand
yeah,
with your little magnifying glass?
all right. So we're going to copy that, and we'll paste it into here, our thorium data. And this calculates the ratio of the thorium that's in the sample, that's 230, to the ratio of the artificial tracer that we add, so we can figure out, so we can measure these isotopes against each other. So those data are in. We can go ahead and close this. And open our uranium data. No, we haven't. Our uranium data are analyzing. That's a nice, smooth, stable signal over time. So far we've measured uranium almost 200 times. That's more than enough to get uh, an idea of how old it is. I'll let it keep running because the longer it runs, the more precise the age is going to get. But at least we can tell the age at this point.
And so you have confirmed that this level of ice or whatever it was formed 4,000 years ago, immediately after the flood.
Yeah, if we get an age of 4,000, that's going to be tricky. I'll be in trouble then because I just contradicted myself. Okay, so we copy this into here. We copy this into here. And finally, we copy this into here. And now here's the magic button. Press to calculate age. It's going to take all those data and, using the radioactive decay equations, figure out how old this is. Are you ready?
Okay.
Ooh, we're close. That is 12,900 years.
You
Actually,
you predicted. Oh,
we
I
have
remember you
that's
had
for the
you had in
difference.
your range 12,900 would be in your range, but I can't remember the exact number. I forgot to write it down.
So I said 12,850. This is 12,900 plus or minus 70 years. So there's an error margin, right?
Yeah.
Take into account. We're going to get that error bar down by running this sample longer, but you can see um, this works.
Outstanding. And it works over and over again at any lab for every sample around the world all the time.
I'll always add my caveats. Like the chemistry preparation process, it has a lot of room for error. Like you have a lot of room to make mistakes. I screwed up a couple samples already. By screwing up, I mean uh, adding the wrong acid. It's hard. You got to transfer stuff between little vials and beakers. And
Granted, but the point is that you've got experience doing this, and it's not just you. There's
right,
all these other labs. There's however many times you've done this yourself, and I know a number of other people that I've talked to who also do this, to do the same work, but they're in South Africa or wherever, and so they're all around the world, and there's hundreds of examples where you can confirm these dates. So when you say that, for anybody who wants to say that all of the dating methods, and I mean all of the isotopes, everything, every type of isotope you could study in every lab, everywhere around the world, every university, everybody's wrong. It's just my favorite book of fables that's right, no matter what. That gets a little bit ridiculous.
yeah. And, I want to emphasize again, we uh, we base this off of the oxygen isotope signal in our sample versus the oxygen isotopes record in Greenland. That one's dated by counting layers. This one's dated by assuming that the decay rates have not changed, right? That they didn't magically change during some time in the past. If that happened, by the way, then we would see evidence for that in all these other numbers, because it would upset completely this uranium series of 238 uranium to 234 to 230 down to 226 and so forth. I mean, it would put everything out of whack, and none of these data would make sense if those decay rates had changed substantially. That's what's cool about this method, I think. So yeah, but here you've got an example of where we can make a prediction based on another record and using a completely independent method, see if this age is robust, right? So I showed you that red line on the graph that marks the beginning of the Younger Dryas at 12,850 to 12,900 years, and our sample is well within error of that.
Outstanding. I'm glad that you contacted me to say, hey, I'm doing this cool thing. Can we record it? So this was a good idea. Thank you for
Yeah.
the invitation.
No, thanks for having me, and now you can see what it looks like. uh, I've got about 15 more samples to do today, so this is going to be a nice one. I think I was here 14 hours yesterday.
Ooh.
So it's a tight, but um, and this lab is one of the best in the world. They've got this.
You work in Austria, right? Normally,
I do.
but
Uh,
did I hear you right? Are you in China now?
that's correct.
Okay.
So we've got a long time partnership. A lot of labs do with this one. Because, like I said, and this is the very lab where they determine those half-lives of 234 uranium and 230 thorium. By the way, it's quite top-notch, and so a lot of visitors come here to do the lab work, and they've graciously hosted me, to run all of my samples. And I wish I could show you all the others too. I'll just say that they worked out really well, and I have a couple others that also cover this Younger Dryas period. Um, and we do get those same ages. The oldest sample I dated while I've been here is about 500 to 600,000 years. So these extend back pretty far.
And
And we can,
these are all rocks that were found embedded in ice cores. Am I understanding that
oh,
correctly?
these are rocks that formed in caves. I mean, these are stalagmites.
Okay.
So growing inside of caves by dripping water. So that's the connection. In Greenland, it falls as snow and compacts down into ice. The precipitation in Europe, it will fall as rain or snow, and it melts and infiltrates through the ground, and it drips down and forms a stalagmite, one layer at a time. So we are determining the age of those layers in the stalagmite. which are too small for us to count. It grows very slowly, only a few microns per year. So typically it's too slow to count visibly. Not always. You get some nice fast-growing samples too, but this is why we rely on uranium thorium chemistry to figure out how old those are. But what's fascinating is like this, in both cases, the oxygen is coming from the atmosphere. It's coming from water in the atmosphere, dropping in this place versus that place. Right? So that's what we've trapped, is oxygen from rain and snow, almost 12,000 years ago.
Outstanding. Dr. Jonathan Baker can be found on Age of Rocks. I will put all of his necessary links below.
Thank you.
Happy to, I'm glad you presented this idea. This was a good one to do.
Cool. I appreciate it. And follow up in the comments with questions. I will keep watch and happy to answer them as best I can.